All right, so let's get started. So this chapter has been all about aromaticity. Let's just kind of take a step back and review what we discussed last class, sort of the underlying kind of idea behind this concept of aromaticity. All right, so in covalent bonds, electrons live in what we call bonding orbitals. Okay. So an orbital, kind of how I think of an orbital, is like an electron cage, right? The electrons are confined to this one particular region within that bond. We call that an orbital, okay? And again, I kind of think about it like a little cage that these electrons are trapped in. All right, so when we say orbital, we can think of that simply as an electron cage. Okay, so within a covalent bond, electrons live in bonding orbitals. When what we call pi bonding orbitals, remember pi bonds are those that we find in double bonds, so pi bonds, double bonds. So when pi bonding orbitals are oriented next to one another, they become what we call conjugated. Right? So when we have these pi bonding orbitals, which is what we see in double bonds, when those pi bonding orbitals are oriented right next to one another, they become conjugated, right? And that means that the electrons are allowed to delocalize, to diffuse across all of those orbitals, right? They become conjugated, which means that the electrons can delocalize or move across all those bonding orbitals. All right, this is this very weird quantum behavior of electrons, this idea that they can diffuse, delocalize themselves, be in multiple positions at once. But yeah, I mean, that was sort of, I know we sort of threw a lot of new terminology out there last time, but again, just to kind of review, electrons live in orbitals, right? When they're in a covalent bond, we call them bonding orbitals. When you have a double bond, we call those pi bonds. And when pi bonds are oriented right next to one another, they become conjugated. And that means that those electrons can delocalize across all those conjugated orbitals, right? And so that was sort of pictured for our benzene. We look at these pi bonding orbitals here, and again, the whole idea is that since they're oriented all right next to one another, any electron that lives in any one of these can sort of diffuse itself around to any of the other ones, right? Can delocalize or move about. This is this basis of aromaticity. We had these two rules as to what made an aromatic compound. First, you needed to have a fully conjugated ring, right? So a ring with all those orbitals stacked up right next to each other for the electrons to kind of move about. All right, but then to be aromatic, there was this other kind of a little bit more counterintuitive concept, which is the number of electron pairs in that ring had to be odd. All right. If you weren't a ring or you weren't a fully conjugated ring, we called that non-aromatic, right? So things that violate rule 1, we call non-aromatic. Things that satisfy rule 1, so they got a fully conjugated ring, but then there's an odd number, or rather an even number of electron pairs, we call those anti-aromatic compounds. All right, and so this was sort of the focus of last class, was given a compound, can you classify it as aromatic, non-aromatic, or anti-aromatic? All right, and so just to review here, let's just do 2 simple examples. All right, so we got to go through and apply these 2 rules. All right, so first we're going to look for a fully conjugated ring. And again, the conjugation can be kind of hard to see. So what I've sort of told you guys to do is to go through and sort of highlight or circle, if you're using a pencil and paper, right? Just each carbon that has a double bond associated with it. All right, so this one has a double bond. This one has a double bond. Boom, boom. These ones at these intersections are particularly difficult to see, but again, I can color them because they definitely have a double bond associated with them. So then I'm just going to keep on going. All right, and so it's kind of tricky to see, again, especially at these intersections here, but you just want to convince yourselves that those carbons do have a double bond. All right, and so I actually, for this particular example, have this massive network of conjugation here, right? A lot of these carbons are all stacked up right next to each other. So indeed, in terms of my first rule, rule 1, we can say check, check. I got a fully conjugated ring. So then I'm going to go through and count the number of electron pairs, counting my double bonds. 1, 2, 3, 4, 5, 6, 7. And so does that satisfy rule 2? Yes. Right? I need an odd number. And so check, check. So both of those are satisfied. So that's what makes this compound aromatic. Right? Fully conjugated ring with an odd number of electron pairs. All right, so then for this one, I'm going to do the same thing, same two rules, right? I'm going to highlight all carbons that have a double bond associated with it. What about this one? No, this one doesn't have a double bond, right? So this is what's going to mess everything up. This breaks my conjugation, and so in terms of rule 1, that fails. And so this compound would be non-aromatic. Okay, and then the last thing that we learned about last class was, well, what about carbocations, right? So what if we have a carbon with a positive charge? These are kind of these special cases here because carbocations actually have empty p orbitals associated with them, which means that they do not break the conjugation of a ring. So for example, we have our non-aromatic cyclopentene here, right? We said that this one was non-aromatic because we had this carbon up at the top that messes everything up. But if I had the same compound, but then up at the top, that top carbon was a carbocation, then when I go to apply those two rules, I'm going to see if my ring's fully conjugated. I got this one here and this one. But again, we're going to count carbocations as well. They do not break the conjugation of the ring. So I get to color this one as well. So this would be an example of a fully conjugated ring, all right, because I got a carbocation with its empty p orbital. So then I get to move on to rule 2. I have only one pair of electrons here, and that's an odd number, right? Cool. So this compound would be aromatic. Okay, so again, we got those two rules, and then we got to keep in mind for carbocations here, carbocations do not break the conjugation in a ring, so when we're going and circling our carbons, we're going to circle carbons that are associated with double bonds, but we're also going to circle carbocation carbons. All right, but they don't have any electrons associated with them, right? So when I was counting electron pairs, I still just counted that one pair from my double bond. All right. So now last thing we got to tack onto this is how we deal with lone pairs. Okay. Let's see. Okay, oh, cool. Oh, all right, so first, I want you all to do these first two for me here. Tell me whether these two compounds are aromatic, anti-aromatic, or non-aromatic. All right, so we got cyclopentadiene, we got one with the carbocation, and then what we're going to learn how to do here, which we don't know yet, is what if instead of a carbocation, it's a carbanion with its lone pair. Okay, I can reset that. I thought that was just up until the carbocations. All right, so for this first one, what do we think? Non-aromatic, right? I got these ones, awesome, but then I have this thing up top, messing everything up. All right, not a fully conjugated ring. This is non-aromatic. And then if there's a carbocation up there instead, now all of a sudden I am going to circle that carbon. So this does not break my fully conjugated ring. So then I get to move on to the next step, counting electron pairs. I have 2 pairs of electrons, so that makes this anti-aromatic. All right, so then how the heck are we supposed to deal with a lone pair? So for lone pairs, first of all, unlike carbocations, right, when we look at carbocations, we said, although I just lost it, we said that there are no electrons associated with a carbocation, right? So when we were counting our total number of electrons, we didn't count any for a carbocation. Lone pairs, believe it or not, there is a pair of electrons, right? So we will count those electrons. So a pair of electrons gets counted towards our total. Okay? But the weird thing about about lone pairs is lone pairs get to decide whether or not they're going to participate in that ring. Okay? They get to choose. Now, obviously, they're not like sentient beings, but it's like an energy argument, but nonetheless. So, lone pairs get to choose. They get to choose whether or not they're going to participate in the conjugated ring. All right, get to choose whether or not to participate in conjugation. All right, and they will only do so if it makes the ring aromatic. So, we get to this compound here. We're figuring out our conjugation. Of course, I'm going to color these 4 carbons here. I get to this lone pair. This lone pair gets to decide. It's going to choose whether or not it's conjugated, whether or not it's going to participate in that ring. Okay? And it's only going to do so if by doing that it would make the ring aromatic. Right? So I can't color this one yet until I go through and count, because I got to see whether or not that lone pair is going to be involved in that ring. Right? And again, it'll only do it if it makes the ring aromatic. So I have 1, 2, this lone pair would make 3. So if that lone pair joins into that ring, is it going to be aromatic or anti-aromatic? Aromatic, right? So in this case, this one will join the party. All right? It'll come in, and so that makes this compound here aromatic. That doesn't work if it's
two bonds. So like this example here.
This one right here?
Yeah.
It's anti-aromatic because there's an odd number of electron pairs and there's no electrons associated with a carbocation. Right? It's just like an empty p orbital. It can be there for electrons can diffuse through it, but it didn't bring any electrons to the table itself, right? As opposed to a lone pair, which does have a pair, it does bring some electrons in there, so it counts towards our total. All right, so again, it's only going to do so if it makes the ring aromatic. I'm just going to erase this here so that I have some room. Well, then what about this example here, okay, so again, I'm going to apply our two rules. I'm going to figure out, all right, these ones are definitely going to get circled. But now I get to this lone pair. I have to figure out whether if that joins the party, that'll make this aromatic. So I'm going to count. I have 1. If this lone pair gets counted as well, that's 2. So would that make that compound aromatic? No, all right? So in this case, so if it doesn't make the compound aromatic, the lone pair is just not going to join the party. It's just going to stay out of the ring altogether, right? So then I'm going to cross this one out. I no longer have a fully conjugated ring. Okay, so this one would be non-aromatic. It's not anti-aromatic because that lone pair just points another direction. It just sticks itself, like literally orients itself in space out of the ring. Okay, so it makes that ring non-aromatic. So the lone pair gets to choose. It will only participate if it makes the ring aromatic. If not, lone pair will not join. Will not join our ring, and thus it will be non-aromatic. Notice that means that it can never be anti-aromatic with the lone pair. The lone pair just will stick in another direction. It will never be anti-aromatic if you have that lone pair. That lone pair is going to choose, and it's only going to join the ring if it makes that ring aromatic. What's up?
So when we have the negative one, it'll only be non-aromatic or aromatic?
Correct. If you have a lone pair, it'll either be non-aromatic or aromatic. Yep. Lone pairs will never make an anti-aromatic compound.
Seems like the lone pair only works when it's even, right?
The lone, yeah, if you have it, if the other number of bonds is even, then that lone pair counts as the next odd number. Yeah, exactly.
So are we technically talking about carbon ions?
Carbanions are a source of lone pair. What we're going to do here is another example with what are called heteroatom. Nitrogens and oxygens also have lone pairs, right? So you can have aromatic or non-aromatic compounds that have these other atoms as well, right? So same logic applies as it does for carbanions, but let's see if we can do this one here. So now we have this oxygen. Actually, we're going to do nitrogen first. Nitrogen, when it's neutral, right, has a lone pair associated with it. Okay, so take a second and see if you can't classify this compound as being aromatic, anti-aromatic, or non-aromatic. All right, so I'm going to go through. I'm going to highlight these carbons because they have a double bond associated with it. I don't know whether the nitrogen is going to participate or not, right? Before I can figure that out, because it has this lone pair, I got to count. So this would be 1, 2. That lone pair on that nitrogen would make 3. So is it going to join the ring or not?
Yes.
Yeah, right? So now all of a sudden I have my fully conjugated ring with my odd number of electron pairs. So this is indeed aromatic. Okay? And so the other thing that we talked about was we can count the number of delocalized pi electrons. But now we can also count the number of delocalized lone pair electrons. All right, how many delocalized pi electrons are there? Counting total number of electrons now, right? Each bond contains how many? Two? These are my 2 pi bonds, right? This right here is not a pi bond, it's a lone pair of electrons. So I have 2 pi bonds, each containing 2 electrons. So that gives me a total of 4. These 4 right there are my delocalized pi electrons. The other ones, I do have 6 total in this ring. The other 2, this pair right here, those are a delocalized lone pair of electrons. All right, but then just for completeness, let's take this other example that we did. We had said that this compound here was non-aromatic, right? So, in this case, these aren't going to be delocalized, but what we would call localized lone pair electrons. Right? So for this compound here, because this pair of electrons is not participating in that ring, it's what we call a localized pair of electrons, meaning it's going to stay put, stay exactly where it is. Right? The whole idea of delocalized electrons is that they spread themselves out across all of those conjugated bonds. If it's not participating in the ring, it's what's called a localized pair of electrons. All right, and so last thing for this particular example, this one's a little tricky, but what about this pi bonding pair of electrons here? Is it localized or delocalized?
It's going to be quite local, or no?
Has it got anywhere else to go?
No.
It's stuck, right? There's no neighbors that it can spread itself out to. So in this case, this pi bonding pair of electrons, because there are no next door neighbor carbons for it to move over to, this would be considered a localized pair of pi bonding electrons. Whoops, 2. So there are no delocalized electrons at all in that particular structure. What's up?
Which 2 are the 2 delocalized lone pair of electrons?
In this original compound?
Yeah.
This pair right here, the lone pair on the nitrogen, is delocalized.
Is that just 1 pair or is it 2 pairs?
It is 1 pair. Each pair contains 2 electrons, right? So I'm asking for the total number of electrons, not number of pairs.
Okay.
Which I know is kind of a subtle point, so we're going to stick to that same sort of format for homework assignments and everything like that. right, so just to kind of clean this up. In our original compound, this aromatic compound, there were 4 delocalized pi electrons and 2 delocalized lone pair electrons, right? Those 6 electrons are spreading themselves out across that whole ring. In our other compound, because it was non-aromatic, that pair of electrons is localized. And because it's just one double bond instead of a bunch of them next to one another, that pair of electrons in that pi bond is also localized. All right, so we're going to practice this a bunch here, but let's just take a second and talk about what it means to be aromatic versus anti-aromatic in terms of the stability of a compound. All right, so let's just take a ring, a 6-membered ring, but instead of making it benzene where I put in a bunch of double bonds, let's just put in one double bond here. We would call this compound what? What functional group is this? An alkene, right? It's got a double bond in there. So this is just an alkene. It is a ring, but it's just got a double bond. We learned about reactions of alkenes last chapter. Alkene. So for example, if I added HBr, we would get what we called an addition reaction, where I get the bromine on one carbon and the hydrogen on the other carbon. So alkenes undergo addition reactions. We learned about a few of them. And notice that when we do our addition reaction, we lose that double bond, right? That double bond is replaced with 2 new single bonds. Now I'm going to take this same compound, or this same ring, but instead of just the one double bond, I'm going to have 3. I'm going to make it benzene. All right, and there's a reason why we distinguish between alkenes and aromatic compounds. Right? We've been talking about these in 2 separate chapters. We put them into 2 different bins. Even though it's really tempting to classify this as an alkene because it's got a bunch of double bonds, we put it in its own special category, which we call aromatics. So this is an aromatic compound. And if we try to do this exact same reaction, what we would see is that absolutely nothing happens. Okay? Unlike alkenes, aromatic compounds do not undergo addition reactions. Okay? Let's just say, for the sake of argument, that we sort of did an analogous reaction here where we broke one of those alkenes. Is my product that I get on the other side, is this aromatic anymore? No, right? Because I broke that double bond, now all of a sudden I've created this non-aromatic compound. Okay, so this is why this reaction does not occur. All right, they do not undergo addition reactions, and that's because aromatic compounds are super stable. There is something special, something magical about being an aromatic compound, that all of a sudden that compound becomes super duper stable. When those electrons can spread themselves out across a ring, it's a very low energy compound. The ability to do that is really, really good, all right? To be honest, the reason why is way above our pay grade for this particular course. It has a lot to do with like quantum mechanical calculations and all that crap, right? Where you're actually doing math with these orbitals. We're not doing any of that math here, right? This isn't a quantum mechanics course. So, bottom line is, aromatic, super duper stable. That's what we gotta remember. Okay? There's just something magical about being aromatic that leads to that compound being very, very stable. So benzene, it's not going to break that double bond to become a non-aromatic compound. It's super, super stable as an aromatic compound. Okay? That's not to say that there aren't any reactions that we're going to learn about for benzene. We will learn about some reactions, but they're not going to break the aromaticity of that ring, right? The whole shtick is that network of conjugated bonds, super, super stable. Okay? Now, it gets even weirder, because then if we take something like this, is this aromatic, anti-aromatic, or non-aromatic? So this would be anti-aromatic. And if we try to do the same reaction, we would see that aromatic, or rather anti-aromatic compounds do undergo addition reactions, just like alkenes. It's not that the reaction is stabilized, it's the stability of that anti-aromatic compound itself. It's a much higher energy compound, all right? So this is a little bizarre, but remember we had two rules for being aromatic. First of all, you had to be the ring, right? You had to be that fully conjugated ring, okay? And that kind of made sense because the electrons have to move around. Okay, check. But then there was this other rule that's seems like it's much more out of left field, which was that the number of electron pairs had to be odd. If they were even, we threw it into a separate bin here, okay? And we called that anti-aromatic. It turns out that anti-aromatic compounds are the exact opposite of aromatic compounds. Anti-aromatic compounds are super unstable. So they are highly reactive compounds. All right, and again, way above our pay grade in terms of explaining why anti-aromatic is unstable and aromatic is stable. It again has a lot to do with just the quantum mechanical calculations behind it. So again, we're going to kind of boil it down to one simple rule, which is aromatic, super stable, anti-aromatic, super unstable. Okay? So these are highly reactive. They are much more unstable. And so that just kind of to go back here explains why lone pairs get to choose, and they're only going to participate if it makes the ring aromatic. They're not going to make this super unstable anti-aromatic compound. They'll just stay out of it altogether, be non-aromatic. Okay. So we will talk about reactions of benzene, but we're not going to start that today. We're just going to kind of practice what we learned about lone pairs and heteroatoms. All right, there is one more thing that we want to do. We used an example with oxygen, or I'm sorry, with nitrogen. Let's do a similar one, but now with oxygen. When oxygen has a formal charge of 0, It has 2 bonds, and how many lone pairs? 2. So, first of all, you're going to tell me if this is aromatic, anti-aromatic, or non-aromatic. All right, but then the last thing that we want to learn, that we want to be able to do is just count electrons. All right, so in addition, tell me how many delocalized pi electrons, delocalized lone pairs, localized lone pairs, and delocalized pi, or I'm sorry, localized pi. All right, so let's do this first one. I'm going to go around. I get to count all of these carbons as being conjugated. Then I get to this oxygen, and I'm not going to be able to count it yet because the lone pair gets to decide, right? So first I got to count electron pairs, see what the choice is going to be here. So 1, 2. This lone pair then would make how many? 3. Okay? And so indeed that lone pair will go ahead and join in order to make this compound aromatic. All right, now, unlike carbocations or nitrogens, oxygen actually has 2 lone pairs of electrons, And there's something important we want to note. Only one lone pair can join the ring. Right? So there will never be a situation where both of those lone pairs are participating in the conjugation of that ring. It's just not possible. It's like a geometry problem here, right? That means that oxygen would have to put both of those orbitals in the exact same place, right? Remember that this whole idea of aromaticity, it comes from the actual like spatial organization of those orbitals. Oxygen can't put those two orbitals in the exact same place, right? So there's just no way for both lone pairs to ever participate in a ring. Only ever going to be one lone pair, right? So in this case here, when we're counting our delocalized electrons, we have 4 of them in the form of a pi bond. 2 delocalized lone pairs, lone pair electrons rather. The other pair is just going to remain localized, right? Not participating in that ring at all. And all of those pi electrons are delocalized, so we got none that are localized. Okay, so again, with oxygen, it's got these 2 lone pairs. It's only ever going to be one of them that participates in the ring. All right, so again, for this one here, I'm going to figure out my ring's conjugation. Cool. I get to oxygen. I got to figure out first whether or not it would make the ring aromatic. So I'm going to count 1, 2, 3, and this lone pair would make 4. So is it going to join in or not? No. And again, it's like you can't count both of them, right? So I'm not able to count both lone pairs. So in this case, oxygen's just going to put both of those lone pairs in a different direction, and this will be non-aromatic. Okay. All right, so then in terms of delocalized lone pair electrons, do I have any in this second compound? No, right? Neither of those lone pairs are going to participate. So I got 0 delocalized lone pair electrons, and all 4 of those lone pair electrons are then localized, right? Neither of them are participating in the ring. What about in terms of delocalized pi electrons? So these ones still lined up next to each other, so they can kind of spread themselves out through this network here. They just can't go all the way around, right? So they're just going to kind of go back and forth and back and forth. So I still have delocalized pi electrons, right? It's just not a fully conjugated ring.